So welcome back, everyone. This is Worksheet 5.1, Carnot Cycle Efficiency and Delta S. And the first part of today's worksheet concerns Carnot cycles, which, if you recall, has 4 strokes. We've got a stroke from position A, and then we've got an expansion down to position B, and then another expansion down to position C, and then we've got a compression to position D, and then a return back to position A like that. And the top and the bottom are the isothermal portions of the Carnot cycle, and the left and the right are the adiabatic portions of the cycle. And so that means that on the adiabatic parts, there is no heat added or removed from the system. But for this top isothermal portion of the cycle, there is heat going in. We can call that Q in. And then in the bottom isothermal portion of the cycle, there's heat going out, and we can call that Q out. And in general, that's going to be different from Q in. All right. So what is the total amount of work done by this cycle? You'll actually calculate this in your homework, and I'm going to give you the answer right now. The answer is that this equals negative NR T hot minus T cold, and then this is multiplied times the log of VB divided by VA, interestingly. And the T hot and T cold refer to the temperatures of the hot and cold reservoirs of the engine, and VB and VA refer to the volumes at positions B and position A. And so the amount of heat that comes into the system is going to be equal to NR T hot times the log VB over VA. All right, and we also mentioned when we first started talking about Carnot engines that they have a certain efficiency, and that is how much work we're able to get out of the system for the given amount of heat that we put in. And so since it's the work going out, then we've got to do negative W cycle. It's the amount of work that the system is expending divided by how much heat that we put into the cycle. And we can just plug in the values we have up here into that equation right there, and we get positive NR T hot minus T cold log VB over VA, and then the amount of heat that's put into the system is nRT hot times the log VB over VA. And notice that these two will just cancel out, so will the NR, and we're left with the efficiency being the temperature of the hot reservoir minus the temperature of the cold reservoir divided by T hot. All right, and we will see that this is why an engine with the temperature of the cold reservoir at absolute 0 has perfect efficiency. And therefore if you set T cold equal to 0, then you get T hot divided by T hot, and so that's an efficiency of 1, which is perfect efficiency. But in general, epsilon, the efficiency, is equal to T hot divided by T hot minus T cold divided by T hot, and that's just me rearranging this equation up here. Then this just becomes 1 minus T cold divided by T hot, and this is always going to be less than 1 because it is impossible in practice to attain absolute 0 in a system, according to the third law, which we're coming up to pretty soon here. All right, let's take a look at the second half of this worksheet now. I'm going to review a few of the equations that we've already seen and then introduce a couple of new ones too. We saw that for an ideal gas at constant volume, a small change in entropy is equal to dq divided by T, and this is reversible. And we can say that the reversible heat is just equal to the constant volume heat capacity divided by T times a small change in T. And then when you integrate that, you get that this equals CV log T2 divided by T1. That's a constant volume situation. But if we have a constant temperature situation, we saw that this equals a change in heat. This is the second law, and divided by temperature, and then we've got this corresponds to a negative change in reversible work divided by temperature. This equals NR log V2 divided by V1. All right, and then you haven't seen this one yet, but I'll show you how you would do the calculation at constant pressure. And it's very similar to the calculation you would do with constant volume. This just becomes dqp rev, so that's the constant pressure reversible heat, dt. And then if you plug this into a similar procedure that we did with the constant volume process, this just becomes Cp divided by T dt. And then when you integrate that over a large change in temperature, then what you finally end up with is Cp log T2 over T1. And if you combine these together, if we've got a process that involves both a change in temperature and a change in volume, then you can just add them together, because it is a state function after all. So delta S just becomes NR log V2 over V1 plus CV log T2 over T1. And for a constant pressure process, the same thing applies. Delta S then equals NR log P1 over P2 plus Cp log T2 over T1. And finally, we can consider a phase change, which obviously wouldn't apply to an ideal gas, but applies in general. If we think of the melting of H2O, and remember that fusion is another word for melting, a transition from the solid to the liquid state. Let's assume that this is happening at constant temperature and also at constant pressure, which is a valid assumption for a phase change that might occur in the laboratory. Then our entropy of fusion is going to be an integral over our heat of fusion, and that's reversible, even though I'm not listing it. And since the temperature is constant, I can just pull that out, and then I get an integral over the heat of fusion. But since I only have dq inside there, then this whole thing just becomes the heat of fusion divided by T. And if this is a constant pressure process, this merely equals the change of enthalpy of fusion divided by T. And that's it.